Um, Today we're doing continuations. It's the Swiss Army knife of flow control. All right, so we're gonna talk about this special thing called continuations that is part of the programming language scheme that allows you to do all sorts of amazing flow control. So a little bit about me, because I don't know a lot of you all. I'm the chief nerd in charge at New Medio. I'm the part-time as the director of the Blythe Institute. I run a publishing thing called BP Learning. As you can see, I've authored or contributed to a number of books. My most recent one is Calculus from the Ground Up, so if anyone's ever wanted to learn calculus, I highly suggest it. I'm an educator at a homeschool co-op called Classical Conversations. I co-pastor Reunion Family Church, and I'm a husband and dad. So here's the image credits. I didn't want to put image credits every place I had the images, so there they are at the beginning. So flow control. All right, flow control is how control moves around a computer program. And there's a lot of flow control that we're used to. Typical structures you might have run into are jump instructions, whether it's a go-to, a function, a while. There's conditional statements, if then else, early exit, break, continue, skip. All these things are changing where the code's going to execute next. There's exception handling, try, throw, catch, lazy evaluation, threading, generators, and there's still others. So anything that changes basically where your program is going to go next is a flow control structure. So that's kind of what we're going to be talking about. We're going to be talking about continuations and how you can use them to build a wide variety of different flow control structures. But since continuations are native to Scheme and most people don't know Scheme, we're going to start out with a quick Scheme introduction. So Scheme basics. So here's how expressions work. So you can see that rather than in most languages you have the function name and then you have your parentheses and then the arguments. In Scheme, it's just a list where the first parameter is the function. So we have plus 2, 3. So that applies the function plus to the arguments 2 and 3. And so you can see that it's very nice because there's no order of operations in Scheme because everything is explicitly defined by parentheses. So it's impossible for it to be ambiguous what order it's going to execute things in. You can define global variables using the define syntax. This in the middle of the screen, you'll see the let, and that's how you do local variables. And so you see A, B, and C are defined, and then in the next block, they're used. Okay, and so in Scheme, parentheses are always balanced. So you always have an in parenthesis for every starting one. And just kind of a typical Scheme syntax, you'll notice at the end of the let over there, you've got this one hanging off that goes to that let at the beginning. So I try to indent it so you can see how everything fits together. So then you can see an if-else there. And so this defines Z to say if Q is greater than 100, then we'll add 5 and 4, else we'll multiply 2 and 2. And whichever one that happens will get put in Z. So everything is a procedure. If statements are like procedures, and they all have return values. Okay. So you define functions like this. So this defines a function that will square a number. Given x, it multiplies x times x. So that's the square function. So lambda basically creates the function. All right, we're a Tulsa lambda lunch. So lambda is what creates functions. And then so there's a separation between creating the function and defining the name of the function. So the lambda x actually creates the function, and then after it creates it, it assigns it to the word square. So from here on out, we use the word square to call the function. Is everyone following that so far? All right. So now you don't even technically need a name for a function. Now these days, anonymous functions are pretty common. Back when Scheme was developed, they actually weren't. So like here we have the same function, but we just, so the red part, the lambda x multiply x by x will return a function, and that function will then be the first thing that's executed for the outer parentheses. So that's the function so that function will then be applied to 5. and so that will return 25. You can do recursive functions, so you do a definition of a function. So here's the factorial function. Factorial, for those of you who aren't math people, factorial of 5 is 5 times 4 times 3 times 2 times 1. Right? So that's so factorial, you get a function that takes a variable. If x is less than 1, we return 1. Otherwise, we multiply that variable times the factorial of x minus 1. Okay? So factorial of 4 yields 24 because 4 times 3 times 2 times 1 is 24. All right? Make sense so far? Okay, so scheme data types. So a list is kind of one of the core data types. You can define a static list by putting a quote mark in front of a parenthetical statement. That basically means that this literally is a list. Otherwise, it would try to apply 1 to 2, 3, 4 and give you an error because 1 is not a function. But with the quote mark, it says, give this all back to me as a list. However, if I have variables and I want to put them into a list, then I use the list command. That's what's on the next one. So if I say list A, B, C, D, that'll take the values of A, B, C, and D and throw them all into a list. The empty list is just a quote with open close parens. That is used as a null value, which is a terminator in all sorts of situations in Scheme. And then there's a function called first. Now, if you're an old Scheme or list person, this is traditionally known as car, but no one knows what that means, so I redefined it to be first. So that gives you the first element of a list. And then rest gives you all the elements of the list that are not the first element. So the first of static list gives you 1, and rest of static list gives you 2, 3, 4. Okay. So you can create a list by constructing the cons operator. Cons 0 and static list will create a new list by starting with 0 and the remaining being static list. And then you can use the map function, like in most programming languages these days. You can so here we map the function. We'll double each value and we apply it to the bigger lists, and that will give us this 0, 2, 4, 6, 8 below. All right. So you also have true and false. True is pound T, false is pound F. You can do symbols with a single quote in front of text. You can do strings with a double quote around text. All right. So I also do all of my programs in here. You can assume are prefixed with this preamble, which simply makes a lot of things shorter and more easy to read. All right. So with that intro to Scheme out of the way, we want to talk about the stack. And what I found is that if you program long enough, you're familiar with the stack, but a lot of new programmers aren't. So I want to just give a quick introduction to the stack and what it is and what it means. So every time you call a function, so the stack is kind of a temporary holding space for all of your current data. And so every time you call a function, it creates a new stack frame that it sticks on top of the stack. And the stack frame essentially holds 3 things. It holds the return address, where you're going to go back to when your current function returns. It holds your parameters that are sent into the function, and it holds any local variables that you've established. Okay? And so this is like, whenever you do recursive function calls, this is how the names of the variables don't get confused. Because each instance of your function is actually in its own stack frame. So it has its own copy of local variables and its own destination of where it's going to return to. So here's an example. So here's our factorial function. Okay. So when we start out, we can I mean the stack probably has things, but we can think of the stack as empty. So we defined factorial as this function up here, and then we call it. So as soon as you call factorial 4, it creates a new entry, a new stack frame entry. Okay, and this, so the arrow is where the return address is going. The return address is going to where we called it from. That's how it knows how to get back. Now we're actually starting up where it says lambda x. And so since x is a parameter, x gets stuck on the stack frame with the value we called it with. So x is 4, and that's in our stack frame. So this goes on. It checks to see if x is less than 1. It's not. So it multiplies x by the factorial of x minus 1. Well, it's calling factorial again, so we're going to add a new stack frame. Okay, so this calls factorial again. Our return address now points to where that's going to return to. And then we now have a new value of x, which is 3. So it's going to run the same code, but now we're using this new x as our current x value. So it's going to do it again. When we do factorial of x minus 1, we're going to get another return address pointing to the same part of the code. X is going to be 2, x is going to be 1, x is going to be 0, and when x is 0, we're going to see that, yes, x is now less than 1, so we're going to return 1. Now, when it says return, you don't know where your function is called from, but the stack does, okay? Because your function could be called from anywhere in your code, so it uses the stack to find out how to get back. So the return address tells you where to send this 1. So where does the 1 go? The 1 goes back to this multiplication. And so you pop off, when you do a return, it pops off the last stack frame and then moves to where it was. And then it does the multiplication and returns it. And then it does the multiplication and returns it. And does the multiplication and returns it. And it does the multiplication and returns it. And when it returns here, we get our final value of 24. Okay, anyone have any questions on that? Pretty straightforward? Okay, so what is a continuation? Okay, so a continuation is where a function continues on to. Now that is not just a physical place in your code, but that also includes the state of the stack. Okay, so what Scheme allows you to do is to bundle up where you're going to go, both in terms of your stack and in terms of your code location, and return a procedure that when you call that procedure, it goes back to that point. Okay, so it's basically bookmarking both a place in your code and a place in your stack that you can come back to. Okay, so this saving of both your code location and your stack frames allows you to implement a lot of interesting data structures. So let's think about a few of these. So first of all, you have try, throw, catch. Well, what happens when you throw? Right? When you throw, so you have a try block, and your try block basically saves your stack. And when you throw, it reinstantiates your old stack frame. So if you ever tried to access a variable that was defined in a try block from a rescue block, it'll say no. And the reason why it won't let you do that is because that stack frame no longer exists, because it reinstantiated the previous stack frame to do those catches. If you think about multithreading, what happens with multithreading? When you go back and forth between threads, what you're doing is you are reinstantiating the thread, and when you reinstantiate the thread, you're reinstantiating both where it is in your code and what the stack frame looks like. Okay, so we're basically, every time you switch threads, you're saying, okay, we're going to pause, we're going to move my stack frame out of the way, and we're going to put someone else's stack frame in, and going to go back to where they were. And then if a lot of people like the break and continues from loops. What do those do? Well, if it's a pretty deep break, it might actually pull out of your current stack frame and go to a different one. Okay, so these are all different control structures that are based on saving the state of your stack and your location. Okay, so in Scheme, you can do all this with one function called call with current continuation, or as we will call it, call CC. Okay. So in Scheme, a continuation is a function which, if you call it with a single argument, gets rid of the current stack and replaces it with the stack that's in the continuation. Okay? And then it performs the return function using whatever argument you pass to the continuation. So you call the continuation with one argument, and it All right, you call the continuation with one argument, and it'll basically do a return. It'll reinstate the stack, and then do a return from that point with whatever function you defined. Okay, so so we're going to look at a few contrived examples. You might say, what's the point of the examples? There's no point to the examples except to show you how it works. Okay, so here's a simple one. So what this does is this creates a variable called myval. Okay, so then we have call cc, and it will call this function, this next lambda here, and it will pass it the current continuation. And so I called that variable the continuation. Okay, so then I have a display. This will be executed, and then I call the continuation with the value of 5. Okay, so what the continuation does is, so when we called call cc, it then called this function, this lambda function, passing in call cc's continuation in the variable the continuation. So when we call the continuation 5, it returns from call cc the value 5. Okay, so right here we're doing an early exit. We're saying the continuation 5, and it poofs back out to the place where we define the continuation. And so myval now has 5. So this is the output. It'll say this will be executed, and it says 5. It does not do this display because the continuation pops you back out. So basically the call cc saves the current stack into the function the continuation, and then we reinstate the save stack with the return value, and that return value goes to myval. All right, does that make sense to everyone? All right, so here's another contrived example, and this is you can actually return continuations. So here I set myval to be a continuation. So we create this continuation, right? So this holds the stack as it currently exists. And then what we're going to do is, rather than use it, we're going to return it outside, right? So we're returning it to myval. So myval has a continuation that if we call it, will return back into myval. So it's a little kind of weird to think about, but you'll see how this works. So continuations are in fact procedures. So this checks to see if myval is a procedure. Okay, if myval is a procedure, we'll say, okay, well this is a continuation. Say, okay, well this is our first time through. And we'll say myval is a continuation object, and then we will call myval5. And so what this does, so remember the continuation saves the stack frame so that when we call this function, it will return back into here. So when we call myval5, it'll act like we were right here and return the value 5. Okay, so now myval, instead of having a continuation, now myval has 5, and we're starting all over again. So then we say, is myval a procedure? Well, no, it's not. Now myval is 5 because that's what we invoke the continuation with. So now it'll run on the false branch, and this is the final output. So the first time through, myval is a continuation object. Second time through, myval is 5. So we didn't have any loops or anything. We created a continuation, and then we called the continuation. Okay. So that's the basics of how continuations work. So let's now look at some actual practical examples of what we can do with this. So if you remember from my previous scheme talk, one of the great things about scheme is the amount of things that you can do with a small number of lines. We did all sorts of cool things with a small number of lines in the previous talk. We also talked about how the fact that the scheme specification itself is like 50 pages long, including its library, its standard library, while C++ is somewhere around 1,000 pages long without its standard library. So it's a very small language, and you can also write very small programs with it. It's very easy to extend. So the first thing we're going to talk about is cooperative multithreading. So what is cooperative multithreading? That's just like your standard multithreading, except that you have to explicitly say when you're going to yield to another thread. So Preemptive multithreading is when the CPU gets to decide for you when you yield to another thread. But cooperative multithreading is when you have to just say yield. So here's our API that we're going to develop. And so we're going to have thread new. We'll create a new thread with a procedure to run on that new thread. Thread yield will yield control to a different thread, and thread end will terminate the current thread. All right, does that make sense to everyone? All right, so here is an example program that we could build from this API. And so we'll define these three functions, T1, T2, and T3. And these alternate doing stuff and yielding to other threads. And then all we'll do is create new threads with each of these procedures, and then end the current thread. The one thing about this is that you do have to do a thread end at the end of your program for this to work. But anyway, so here's your output. You can see there's intermixing from the different threads. Okay. So anyway, so you might be surprised that you can actually do this entire threading library in 2 screens of code. We'll show it all right here. So let's think about continuations, how they could be used to keep track of this. So your continuations, you create them to bookmark your current state in each thread. So if you're going to yield your thread, what you do is you simply create a continuation to represent where you are in your thread, and we're going to add it to a queue and then execute the next continuation. And that will pull in the stack and location from the other thread and start it. Okay. So here's the code, and so this is for thread yield. I figured this is kind of the core. We'll talk about creating and ending threads in a minute, but first I just want to talk about the swap over process. So we have a thread list. It'll start empty, and we'll tack onto it as we create new threads. And so the first thing we do is when we call thread yield is we check to see if the thread list is empty. Because if there's no other threads, you know what? We don't need to switch threads if there's no other threads. So we just return. Otherwise, what we're going to do is we're going to save the current thread state into a continuation. And so we're going to do call CC and just save that thread, that continuation, into a local variable. Okay, now once you save that, there's 2 ways that variable can come about. It can either come about from creating the continuation or from calling the continuation. So we have to check to see if we came from the continuation or if we're being called with it. So if we're coming from the continuation, then that means we have to prepare the next thread. Okay, so we grab the first thread from our thread lists, then we get a list of our remaining threads, and we create a new thread list by tacking together our remaining threads and the one that we just saved. So that's what that append does. Tacks together our remaining threads and the one that we just saved. Then we set the thread list to be our new thread list, and then we call the next thread. And so calling that will invoke the continuation. Okay? Now, if we are the thread that's being called, right? Because the 2 options here are that cont variable could be created either by creating the continuation or calling the continuation. And that's what that if procedure does. It checks between those 2 possibilities. So if cont is not a procedure, if instead it's the symbol your turn or whatever it is, then we just return. Okay, so if our thread is the one that was called, we just return. So that's how thread swaps go, and that's just what, 10, 12 lines of code. So then we have how to end a thread, and basically we say if the thread list is empty, then we exit the program. Otherwise, this is basically the code from thread yield, except we did not start by saving our current thread. We just don't care about our current thread anymore. We'll just move on to the next one without saving the current one. So then creating a thread is just like the beginning of the thread yield. We create a continuation for our current state and throw it on the stack, and then start running the code that our procedure code. So that's a full multi-thread. I wouldn't say a full multi-threading library, but it's a half decent multi-threading library done in about 20 lines of code. So that is the power of continuations. So you can also do exception handling. So let's look at some code that we might want to write. So so we might have these try commands, and so I have a try nested within a try, and I'm going to display some stuff. Then I'm going to throw an error, and I'm going to do a catch. If it catches here, it'll do this. But if it doesn't catch, it'll bounce down and do this one. Okay, and so again, I can implement this using continuations. Now, one thing, I cheated a little bit because I added macros to this to save some typing. We talked about macros in the last session, so I'm not going to go over them a lot. But basically, the macros prevent me from having to write a whole bunch of lambdas. Okay, so this is what it looks like without the macros. It's exactly the same, but there's I had to throw in a lot of lambdas to manipulate it. So anyway, so all it takes to implement this is about 2 pages of code. And so you have try, and all try does is it saves the current location as a continuation. And then just as before, we check to see if the continuation came from being the continuation or if it came from the continuation being called. If it came from being the continuation, we set up exception handlers, and then we run the evaluation, and then we unset the exception handlers. If it comes from the continuation being called, then we run our exception handlers, because that's how the throw works. The throw works by invoking the continuation, which will then, if you invoke the continuation, that's like a throw. And so we actually define our throw to simply grab our most recent exception handler, and then call it. And catch, all it does is it looks at the exception data and decides if our exception data matches the kind of thing that we're looking for. So that's it. And then if you want to see the macros, I don't really want to talk about macros today, but just so you know, I'm not faking it out. There's the macro definition. So anyway, so that's a try-catch implementation with 2 screens of code. All right. So with about 4 or 5 screens of code, we've implemented multitasking and try-catch. So then we have logic programming. So logic programming is fun. This is actually one of the reasons why I grew to love continuations. Logic programming allows you to do crazy things like assign variables ambiguous values. So you can say, so this A and B operator says, if I say A and B 1, 2, 3, 4, 5, that will return one of those variables, one of those values. I don't know which, one of them. All right, so it'll return one of those, and then later in your code, you can make assertions. And the code will re-execute and re-execute and re-execute until it finds the set of ambiguous values that satisfy all of your assertions. And so let me show you some code. So here's how you program by assertion. So we're going to set in the first one, we're going to set the variable in to be one of those values. One of the ambiguous values, 1, 2, 3, 4, 5, 6, 7. Then we're going to set s to be n times n. All right, so basically n squared. Now, note that, so then we have assertions about it. Assertion is actually about s. Notice n has our ambiguous value, but we're actually doing assertions about s that knows nothing about the ambiguous values. So we're asserting that s is going to be even and asserting that s is going to be greater than 18, and then we're going to display what n is. And lo and behold, it outputs 6. Because 6 is the number. 6 is the number that will produce an even value that is greater than 18. Okay, so notice that our assertions don't even have to be about the variable that we declared as ambiguous. It just has to be, the assertions could be about anything at all. It'll just keep on retrying different values until it hits a value that makes the assertions true. And so below, we even have 2 ambiguous values. A and B are both ambiguous values, and we are going to assert that a squared is equal to b. Okay? So it's going to go through and try all of our a's and all of our b's until it finds one such that a squared is equal to b. And so the first one outputs 6, and the second one outputs a is 3 and b is 9. Okay? Now if it didn't find any that satisfied the assertions, it'll give you an error. But as long as one of the values satisfies your assertion, it will return that one. If there's multiple, then it generally returns the first one that satisfies it. But logically, it can return any of them. So that's what ambiguous values look like. I'm not going to go through the code that does it because it's kind of messy, kind of convoluted. And the last time I wrote this function, but I wrote it like 7 or 8 years ago, so I don't remember all the ins and outs of it. But it's just one screen. This is the entire code that does that. It basically works by iterating through your list and creating continuations at each point. And there's a failure stack, and every time you call a failure, it invokes the continuation for the next value. And so it just goes through there, and basically for every value, there's a saved stacks location, and every time you go through there, if you fail an assertion, it just calls the continuation, which reinstantiates the stack and the return value with the next one. And it just goes through and goes through and goes through until it finds one that's successful. And it doesn't even have to, there's not actually a specific success notion. It'll just not go back through and try another one if it's successful. So anyway, that's the basics of what we're going over. There's other uses of continuations. You can use them like if you've used Python's generators, where you can basically you can loop through values and just yield values from a loop rather than having it's just a nicer way of programming to yield a stream of values. You can have coroutines, which are actually somewhat like generators, and anything that requires a pause or a resume facility. So there's been like HTTP libraries that are written using continuations, so that your the next request will just re-invoke the continuation to continue your processing. So you can actually do direct like question and answer stuff in your code, so kind of interactivity with the user, and it's just re-invoking your continuation. You don't have to, it doesn't have to look stateless. Your code can actually look stateful as you write it. There's one more function that I'm not going to get into, but it's kind of important if you go into this heavily. That's dynamic wind. And basically, it allows you to run code when a frame becomes active or inactive on the main stack. So if your stack frame, if a continuation call causes your stack frame to be pushed to the side, then it will call one function. If it causes your stack frame to come back into the stack, it'll call another function. So it allows you to do a little bit of cleanup and fun stuff as stack frames are pulled in and out. So in short, continuations are awesome because they do all sorts of crazy flow control. You can make up your own flow control operators. You're limited only by your imagination. And the flow control operators that we tend to use on a daily basis, you can implement with ease using continuations. So, questions?
Do continuations show up in other languages?
Very few. I think ML has them. I'm not sure of any others. One of the problems, what? Oh, OCaml does? Yeah, one of the problems with continuations is that I think it would be really hard to do, well-typed, statically typed continuations. I don't think it'd be impossible, but it'd be difficult. And so a lot of functional programming these days is shipping more towards strongly typed, statically typed stuff.
Ruby.
What?
Ruby.
Ruby has continuations? Are you sure?
It's a kernel module.
I'm surprised.
CC.
There's a continuation compiler plugin for Scala too.
Nice.
Well, of course. Oh.
Not necessarily.
Is there anything that's not oh.
So
Ruby.
Sort of like stack.
So one of the cool things about Scheme is that when you combine macros and all these different tools, you can actually kind of build your own programming language with Scheme. In fact, yeah, it is actually. There's actually a lot of the early computer programming languages books use Scheme, and just there's actually I meant to actually bring the book.
The wizard book.
No, I mean the wizard book. Are you talking about
SISC.
Structure and Interpretation of Computer Programs? That's a great book, but that's not the one I'm thinking of. There's a programming languages book that goes over several programming languages, but it all uses Scheme syntax, and it just shows how they're basically you can write everything as kind of Scheme macros, and you can get all the benefits of different programming languages just rewriting it in Scheme. So because the nice thing about Scheme is because there's basically, you can think of it as although there is a syntax, there's basically not. It's all just parentheses.
Wasn't the guy, was it Norby? That wrote it's been a long time ago, but he basically rewrote the design principles book, the Game of 4 book, using Scheme, and showed that 23 of the 25 principles were not necessary if you use this.
That would be awesome.
Because they're built into the language.
That's cool. I forgot what I was going to say. Oh.
Can this be represented in JavaScript's callback functions?
So it's not really callback functions because you're really reinstating a full, because a callback function doesn't reinstantiate a full stack. Now, what you can do in most languages is there's what's called continuation passing style, and it's where that would be worthy of its own talk. But basically, it's rewriting your own code so that rather than ever returning functions, you just call a new function with the current state. And so you can use that to kind of fake continuations if you really wanted them. But that's kind of a pain in the butt.
Overflow your stack when long enough?
Yeah, probably. Although, I mean, so if you do, so Scheme, another thing that it does is tail call elimination. So whatever your last, it actually, if the last thing that you do in a function is a function call, it actually, instead of actually doing a function call, it actually just rewrites the current stack frame and does a goto. And so that way you actually don't actually lose, you actually don't, if all of your continuations are in tail call position, you actually don't lose that much stack space. So now that what I want, another thing I want to do is, I'm not sure continuations, when you combine continuations and tail call elimination, I imagine somewhere in there's a couple of implementations that probably don't do it right. So I've always been curious if you could break most Scheme implementations by combining tail call elimination and call with current continuation. Chicken Scheme, I don't think would fall for that, because Chicken Scheme, what they do is they actually garbage collect their stack frames. So what typically happens on most programming languages is the stack is kind of just a static area of memory that grows and shrinks. But what they do in Chicken Scheme is your stack frame is actually allocated just like any other object. So it's on the heap rather than on the stack, and then it just garbage collects your stack frames when they're no longer in use. And so anyway, it's a little bit, it takes a little bit of extra time, but not a lot, and it gives you a whole lot of extra flexibility because the compiler doesn't have to care too much about what stack frames are in vogue at the moment.
So it like creates a virtual stack, basically.
Yeah, basically. I mean, so because each stack frame it basically instantiates separately, and then the stack itself is just a list of the current stack frames, and so you can store that list anywhere you store other lists, and then just moving the stack frame just changes one global variable to be pointing at one stack versus another. So anyway, other questions? All right, well, thank you all for your time. Have a good lunch.